Okay, I guess the recording button
Yes.
start. Okay.
It's
Okay, so I would like to welcome you to our webinar number 6 in 2025 in uh, regard to artificial intelligence, AI data-driven seismic facies analysis by Dr. Ayon Day or D?
Day.
D? D.
Day.
Okay.
Day.
Okay, Dr. D.
Yeah.
DEY. Okay, my name is Mazen Hilali. I'm senior petrophysicist working with Lok Oil International West Kunna project in Basra, Iraq. I will leave the floor now to Dr. Mohammed Jawad, VP of Technology with SPWLA, Iraq.
Thank you, Mr. Mazen. Distinguished guests, it's my distinct pleasure to welcome today's session organized by the SPWLA Iraq. My name is Muhammad Jawad Zainul Abidin, and I serve as the VP of Technology for the SPWLA Iraq. I hold a PhD in petroleum engineering and am a senior faculty member in the Department of Petroleum Engineering at the College of Engineering, University of Kirkuk. Today is Wednesday, July 9th, 2025, and we are pleased to present the sixth edition in our ongoing webinar series. This session is entitled Artificial Intelligence Driven Seismic Facies Analysis and will be delivered by Dr. Ayon Kumar Dey, Senior Application Engineer at MathWorks. Welcome again, Dr. Ayon Kumar Dey. Dear attendees, kindly close your cam and mic during the webinar. The session will be recorded. If you have any questions, please feel free to type them in the chat box. The lecturer will answer them during the question and answer segment at the end of the webinar. Additionally, please note that during the presentation, we will share a link in the chat box to join the SPWLA Iraq on LinkedIn. Thank you. And Mr. Mazen, the floor is yours.
Thank you, Dr. Mohammed. Thank you. So let me just present. Okay. Put it on full screen mode. Is it on full screen mode?
It's not sharing.
Not sharing?
Okay, now it is. Yeah, for me.
Okay.
Yeah.
So I would like to welcome again our attendees and to thank our lecturer, Dr. Komar. This will be the sixth webinar in 2025. This year focus is on artificial intelligence application in geoscience and petrophysics domain. This lecture name is Artificial Intelligence AI Driven Seismic Facies Analysis by Dr. Ayon D. We are planning to hold 10th webinar this year. We successfully managed to hold 6 of them. The next webinar supposed to be with Aspen Tech. It is the company that holds Geolog software. It will be about machine learning application in by Geolog petrophysical software. The other webinar will be announced by its time. As every year, we will provide a special learner certificate for any attendees that attend 6 of our webinars to be awarded in December or June early next year. We are very welcome to anybody if you want to join officially Iraq chapter through www.spwla.org. Question and answer to be kept at the end of lecture. Thank you all. And I will keep the floor to Dr. Ayon. He can present himself better than us.
Thank you very much.
You're welcome, Doctor.
I welcome you all to today's webinar. A bit background about me is I was born and raised in Canada. I got my first degree at Memorial University in Eastern Canada in applied mathematics, focusing on industrially applied mathematical modeling, which we now call data science. Then I did my master's at the University of Calgary with the Consortium for Research in Elastic Wave Exploration Seismology. with a specialization in exploration seismology, and then worked in the industry in Canada for GeoX Systems, then Hanson Russell Canada, Husky Energy, and Sasol Canada. Then pursued my PhD with the Delphi Consortium at Delphi University of Technology. Subsequent to that was a visiting scholar at Mauricio Sacchi's Signal Analysis and Imaging Group at the University of Edmonton, or University of Alberta in Edmonton. Then I've worked with Chevron and Amoco, Aramco, and KOC through Halliburton Consulting. Work basins all over Western Canada, Eastern Canada, the United States, North Sea, Middle East, right? Onshore, offshore, clastics, carbonates, and unconventionals, right? So kind of the whole gamut, right? And with that, I'll welcome you today and talk to you a bit about how we can automate facies classification or integrated facies classification using MATLAB. And it's integrated because the critical part of any classification, right, it's still are the labels. And that's where the petrophysicist really comes into play, right? Processing the logs, right? And having the proper, right, let's say, nature, right, in the SP logs, right, the gamma logs, porosity, resistivities, and stuff. Everything that would help us define facies at the point sources on the Earth, and then we use that to help us understand the spatial distribution, right, through an integrated analysis, right? So this is all around sort of the digital transition, right? We all know that the digital age is now, right? And then deep insights reside within our data, right, that inform on challenges when integrating with theory. MathWorks enables navigating this digital landscape by providing end-to-end ecosystems to innovate within this data-driven paradigm. And particularly today, we're going to see how exploiting the full nature of data can help deliver a better result. Right. So to begin, I'd just like to show it's not just MathWorks that's thinking about this. We partner with many different oil companies. Here you see some customer success stories of work we've done with Shell of applying artificial intelligence to geoscience challenges. Right. To the left, you see work we did with Shell to go from the image you see on the left, right, to the depositional architecture, right, the fluvial architecture that you see on the right. And then on the right-hand side here, we see another example with Shell where we took incoming seismic signals and automatically segmented them into P and S waves. And this was all within a carbon capture, right, and sequestration project with Shell, where if there is any microquakes, right, or induced seismology, right, we need to understand that, right? And key to understanding that is separating the P wave and the S wave arrival, right? So these are some examples of other domains, right, and other areas where deep learning is making headway within the industry, right? So many of you know, right? I'm sure that seismic data is a remote sensing data set, right? I'm just showing here the marine case, right, and then the land case. But in both, it's the same experimental design in which energy is propagated into the Earth and then returned to the surface and recorded. And we want to deduce material properties and structures and property distributions in this subsurface from these types of data. Right, so it's right, the reflection, right, is proportional to what we call the impedance contrast, which is how much a rock, right, would resist the energy of the seismic waves traveling through it. And then what we call quantitative interpretation allows you to incorporate this data with petrophysical knowledge, right, and geological knowledge, right, to determine reservoir characteristics and type. Right now, signal seismic is a signal, and to condition it is a signal processing exercise. And many of you know that it is quite intensive, right? So it can take months to a year to maybe more than a year to go from actually getting your data to getting the product that you can work with. So seismic interpretation very generally, right, helps you identify subsurface features. In this particular case, the goal is to go from the data that has been recorded and processed on the top here to some representation of the geological facies and distributions in the subsurface, as we see on the lower part of this slide, right? And this particular data, it's a mix of sand, silt, and mudstones, right, deposited, right, in a deltatic fan, right, at the mouth of a river, right? So typically we call this a deltatic environment, depositional environment, or deltatic facies, right? And the coarse sediments, right, sandy sediments deposited in a meandering river channel or the fluvial environment, right, is the critical, right, or the desirable target rock there, right? And then the extremely fine-grained sediments are deposited in shallow lake beds or lacustrine environments, and they tend to represent seals or blockages to flow, right, baffles. Right. So as we know from our experience, right, that interpretation has many challenges, primarily based around manual interpretation, because this is very time consuming and is very prone to interpretational bias, right? And the reproducibility is challenging. Right. And then we get into the more numerical and quantitative approaches, such as geological modeling, facies extraction. Right. So this approach that I'm going to show you today was developed during the SEAM AI competition a few years ago. I forget the exact acronym for SEAM, seismic, elastic, and acoustic modeling, I do believe, right? It's an SEG, AAPG, SPE joint challenge, I guess, or event, right? So the idea was to take a marine data set from offshore New Zealand over an extensional clastic basin, right, and see if, how the facies, right, therein can be classified, right? So the goal was to develop some sort of machine learning algorithm, right, whether that be shallow or deep, working from the raw 3D image data. So working from this data, how can we get to some representation of the facies? So our strategy was based on signal classification along with CNN, because what we found when we started deep digging into this challenge was that the processes, the methodologies, the case studies were all image-based, right, using the convolutional neural network, right? And while this is correct and a completely valid approach, right, it's only exploiting the image nature of the data. It does not, it completely ignores, right, that fundamentally the seismic image is created from a trace by trace sequence of actual signals, typically accelerometer signals, right? So there is a whole another aspect or dimension to the data that can be exploited, right, and leveraged to help improve our solution. So we decided to take a dual approach, right? We will train a 2D UNet model to exploit the image nature of the seismic data, right? Of course, this has been tied, right, to wells, and we have spot locations where we can check to make sure everything correlates. And then we also decided we would follow that up with training an RNN, a recursive neural net model. These are typically GRU, right, or LSTM architectures, right, that are ideally suited for signals, right, and then we would combine both prediction models, right, to get a final prediction and probabilities. So as we explore the algorithm, right, we can see a bit, right. So this is the lower here is actually a result, right, or sorry, the exact solution that would be chased from the above model. And then this is just showing we loaded some data into a vision, into a segmenter, a volume segmenter, right, just to see, right, how it looks, right. I apologize for this lower left-hand image that should be rotated counterclockwise in 90 degrees. Right, but again, to emphasize, right, the seismic image is fundamentally a sequence of signals. So we're exploiting this nature as well as this nature. So spatially in 2D, the image nature of the data is exploited, while in depth, right, or time, right, so vertical domain, the signal nature of the data is exploited. So for the image, for the 2D version, right, or the slices of the data, we take a semantic segmentation approach, right? So when you kind of dive into the literature for seismic facies or facies interpretation in general, it's been dominated by 2D deep learning models on images. Some examples, right, are shown here, right? And then you can see from Google Scholar keyword search, right, up, it's been dated now, right? It's all seismic facies classification, right? But then when you and then you can see the uptick, right, of machine learning coming into the game. And this is after the demonstration or the boom of CNNs for image analysis. So most of these methods include semantic segmentation using a convolutional neural net, and they tend to exploit a 2D or a 3D method, with the most popular architectures being the UNet architecture and the VGGNet architecture. And here are some references, right, towards how segmentic segmentation is used in 2 and 3D. Right, and for those of you who are interested, just here is a network structure diagram for how semantic segmentation works. It's not the full diagram, but you see sort of at each stage it branches, right? And then you can see many encoders, and then you're going to bridge, and then you're going to have another set of encoders to rebuild, right? And this is what the result of these types of methods, right? So you have the seismic data, you have some labels, the geological interpretation, right, or a petrophysical, right? This could just as easily be. You combine them in a deep learning framework, and you get a pixel by pixel classification of the data. And this is from an AAPG presentation, right, by Daniel Cheretes, who was at Shell at the time, I believe. Right, so a deeper look at the specific network we used was the UNet, right, for semantic segmentation as opposed to the VGG net. And then you can see, right, what happens in this architecture is as you go down the left-hand side, right, you see that there are branches out on the right-hand side. And then it all comes together at different stages and then comes to the final stage. And then some references again about how this works. And this is a methodology we borrowed from our colleagues in medical imaging, which widely engages in image segmentation with very similar data. They typically work with ultrasound data, which is very similar to seismic data, just in much higher frequency ranges. And they have a better experimental design setup usually. And just to highlight, right, that you come in with an image, and then right at the end, right, you compute the probabilities, and then you do the classification outputs. And then the training strategy is you come in with the inlines and the crosslines, right? You do some image pre-processing, some volumetric Gaussian filtering. You might know this as structural filtering, fault enhancement filtering, right? Diffusion filtering. And another critical thing is histogram equalization. And this is normalization for images, much in a very similar way that you would like normalize, right, signal data by removing the mean and scaling by the standard deviation. Histogram equalization is a similar concept for images. Right, so as you can see, right, it draws out, right, higher contrast information. And a critical thing is so as to not bring any kind of genetic relationship bias, right? We want to randomize the patches so that essentially the method can't cheat because it would learn that each successive patch is somehow connected to the previous patch. You want to avoid that, so you do that by randomizing. And each patch is 256 by 256 by 3. Right, so this is what the randomized patching looks like. Okay, and then we train the UNet, and this is just a snapshot, right, a few epochs in, right, but you can see it rapidly drops down, right, the loss rapidly drops down to 0, and then continues to train. Right, so at the time the slide was made, the training was not complete, right? So, but you can see that we have an initial guess, then the upper part gets refined, the lower part gets refined, and then it combines. Now, there are some challenges with this approach. Otherwise, why would we have been brainstorming or thinking about ways to improve it as opposed to just optimizing on the hyperparameters, right? And the regularization of this net, right? So overall, the accuracy tends to be less, right, than a manual or a different type of labeling approach. The input image size really impacts the prediction results. So it is highly important to run an experiment manager and experiment design concepts around the image size to optimize on what would be the best. In MathWorks or in MATLAB, we call this the experiment manager. Other products might have a different terminology, right? And the models are not data agnostic, right? They're very dependent on the input data, and more critically, all the learned features are only based on images, but the underlying data is signals, right? So this is the repeating theme, right? Up until this point, right, exploiting both signal and image nature had not been pursued, right? So again, just to reinforce that, while we have these facies images, they are indeed, right, trace by trace signals, and we can see. Pardon me? Is there a question? I just heard.
No, I have a mute.
Okay, sorry.
Sorry.
And then you can see, right, the signal change, nature changing with the facies, right? So, right, this was to us, it seemed very logical to try and exploit this. So we decided to take a RNN, or recursal neural net approach, which is architectures that are specifically designed, right, for sequence to sequence analysis, and the need of what we call wavelet processing. And this is mathematical wavelets, not the seismic source wavelet. Although the seismic source wavelet could be provided in the system as what we call a mother wavelet, but that is diving a bit deep into the details. And using this approach, we can get an accuracy range of 82 to 96%, depending on how we go, right? I think at the end for this particular work, we achieved the 93% uplift, and then we did some subsequent work, and we were able to increase that to 96%. But then we felt that anything else, right, we were at the limit of overtraining here, and then we decided to stay with the 93% hyperparameters just to ensure against overtraining, right? And then the architectures we explored were everything from gated recursive units all the way to bidirectional LSTMs, right? So long, short-term memory architectures with a memory that can go backwards and forwards because the data is static. So we know what comes after, and we know what comes before our current state. And that needs to be combined with a domain of wavelet processing called wavelet scattering, and specifically the multi-resolution analysis approach of wavelet scattering. Right, so what happens if we just take the raw data in, right, without any sort of wavelet processing, right? And we just took it through this architecture. First, we tried it with the GRU, right, gates, and then by LSTMs eventually. And then when we do this, right, first of all, you see that the accuracy is going cyclically here. So in the most modern approaches, this just took a steady decline learning rate, right? But now we have an understanding that when we see this kind of behavior, we should really use cyclical gated learning rates.
ما فيش ريجستريشن. هو مديني اللينك بتاع جوين ميت وخلاص. جوين ذا ميت.
Can someone translate that question for me, please?
No, it wasn't a question. He
just
forgot the mic open. Sorry.
Okay, no sweat. So yeah, you can see when you look at the confusion matrix, down the diagonal, there's very poor percentages of accuracy, and more importantly, the whole confusion matrix is almost totally populated, and it's populated with more than 50%, right, of error. Okay, so this is not a fruitful path to take. However, right, if we do wavelet processing, right, we can see we get very good, very high validation accuracy, right, along the diagonal, and we really clean up the cross diagonal or the cross variance noise or leakage, right? And how that was done was what we call wavelet multi-resolution analysis. So you come in with the signal, right? Or if you have a very good tie, you could even come in with the tied wavelet seismic source. And then it's always a bifurcation of scales, as you see in the cascades down, with each level, right, having different details, right? And you can see it's a bifurcation of a high pass filter and a low pass filter. And then what gets low passed is then high passed and low passed again, high passed and low passed again, high passed and low passed again. And that's how we extract, right, the details at the different layers. And you can see the bandwidth is there that's coming in, right, into play at the different scale levels. Right, so if we come in with a single seismic trace, and I'm displaying them horizontally instead of vertically, just for slide space reasons. And then we use what's called an FK14 wavelet, right? And we're going to do 4 levels of decomposition. Within MathWorks or within MATLAB, we have a low-code approach to do this, in that there is an app within MATLAB that you can work with to discover what would be an optimal wavelet and what would be optimal levels to decompose. You don't need to code. You can use this app, and then you can just generate the code or the function at the end. So for this particular signal, we see that the background, or what might be considered, let's say, the macroscopic or the regional, right, geology, right, is captured in level 4 decomposition, while level 3 and level 2 add subsequently more detail with higher resolution or wider band, higher resolution. Right, and then you can see that when we reconstruct the signal using just levels 2, 3, and 4, right, we get almost a complete or a perfect reconstruction. And that should not be any surprise, because when you see level 1 is pretty flat, right, and the reconstruction residual, right, is pretty flat. So when we work with recurrent neural networks, first we started with one trace at a time, and that was fine, right? But then we thought about it a bit more, and we know that within the Earth, locally, right, there is spatial correlations, right? So to capture that into our solution network, we expanded from going trace by trace to a 3x3 by in this case 10,006, right, samples in depth or time, right, to do the wavelet multi resolution analysis, so we can capture features that are not only depth of time correlated, but also spatially correlated in X and Y. So as you can see, this very quickly enlarges the data set, right? And makes it 3 times. So we're getting into big data situations here, and this necessitates the need for GPU and cloud computes. Right. So this is one of the architectures we explored. This was one of the BiLSTM architectures, and you can see that as we train, right, very stable and consistent accuracy increase, right, and a very stable, right, loss or error decrease. Excuse me. Right. So then when we look at these results on the validation data, we see that, okay, we came in with this data. The actual provided labels are to the right here. And you can see that the RNN, so the signal-based approach that captures spatial correlation is doing quite well. The challenge remaining is resolving or capturing thin layers, right, at depth. Thin layers shallowly seem to be detected, but at depth they seem to be coming and going, and it is so the expectation is, right, when combined with the image-based nature of the data, this can be improved. Right, and then this is another example, right, of the RNN result. Right, so then when we took test data, completely blind data, right, we see that we're doing pretty good, right, in getting the different facies, and it seems to be kind of at the interfaces of facies. There seems to be some challenges, right, with a few odd misclassifications here and there. It's a bit and it's a bit troublesome at the edges where we tend to have more noise. So now when we combine, right, the unit label prediction with the RNN, right, label prediction. So when we combine the signal approach with the image approach, how well do we do at getting the actual label? Right, so again, right, we do unit prediction in the inline, unit prediction in the cross line, and RNN prediction in depth for time. Then we use a polling algorithm, right, that captures the max score for each class. Whichever class has the highest score will be selected as the facies for that particular pixel. And then we finally predictions in the depth, right, domain. So the final solution, we were able to get 93% accuracy on the validation set. Some performance numbers using cloud computes and deploying to an NVIDIA GPU was about 3 hours, right, with the prediction time. Using the signal-based algorithm was about half the prediction time required for the images. Now, I'd be remiss if I didn't discuss that this does require some pretty intensive and modern, right, computing resources. In MATLAB, you need to have a deep learning toolbox, a wavelet toolbox, a signal processing toolbox, and a computer vision toolbox to handle the signal and image nature of the data. And then we had to accelerate the computing by using an NVIDIA container, right? We used a MATLAB reference architecture for AWS. We used 8 GPUs on a Tesla 5 with 32 megabytes, gigabytes deployed, RAM deployed. and then we use the MATLAB NVIDIA network graphics container. And it was all done on a NVIDIA Quattro, right, RTX with 6,000 GPUs. So the image side needs some significant compute power. And this is an image from NVIDIA of the cluster we we leveraged. And then the final results for the first test for different metrics, right? We ranged from 67.6%, or let's say down here from about 60% accuracy, all the way to 92% accuracy, right? And then on the second test, right, was a bit poorer, right? The range went from from the weighted facies approach was a poor choice, right? Because that only gave us about 36% accuracy. But then the equal weighted facies and the interface weighted facies brought us to like between 74 and 83% accuracy. And you can access the code from this Git. So then to conclude, right, I just want to say that integrating the full nature of the available data enables a higher probability of success by mitigating geological risk. Right, we can predict geological facies. Right, the key takeaways are you need to exploit the image nature of the data, the signal nature of the data, and then combine both for an optimal result. And MATLAB would like to partner with companies to help and assist to initiate, innovate, and inspire. And before I take questions, what I would like to do is run a quick demo for you in MATLAB here. What you see here is a MATLAB live script. This is like a Jupyter notebook or a collaborative coding and analysis environment. So I'm just going to condition my workspace. I'm going to load some data. We're going to visualize the cube. Of course, it opened up the wrong screen. Let me see if I can get it over for you guys. Here we go, and you can come through the data, take a look, right? You can rotate it if you want to change your view. Then we get let's grab a random slice from the test data, right, or the blind data, and let's predict the facies on it. This might take a few minutes, not too long. And so for those of you that are with companies or have access to MATLAB, right? If you're a current subscriber, you have full access to all of these scripts from that Git. So let's visualize, right, some of these predictions and segmentations. Right, so we came in with this data. These are the labels of the facies we predicted, and these are the actual facies, right? So what's interesting to note is This very thin facies here was expected to not be detected, but indeed it's being picked up, right? So that was pretty impressive. And then we see kind of noise interference as these two facies tend to come together. This is another example, right, of where we overlay the predicted and the estimated facies with the colors representing where they don't match. So you can see, right, the challenge is at the interfaces, right? So this is an open area, right, left. Okay, now that we know that we can optimally predict using image and signal nature, how do we better characterize the interface or the geological change regimes? And this is just an example of how it looks with the seismic data. The facies draped over the seismic data, and you can see that the predicted facies very well correlate, right, to where we see changes in the nature of the seismic. Right, and this is another co-visualization image. And some ways to use this are, say, if you were going to design a well. Right, so oh, I don't know, say we wanted to go from here. I don't know why it's not letting me. Try this again. Wrong section. It just worked. This section. Pop that out. There we go. That's why. Say we wanted to design a well. Okay, this, please forgive my very coarse and inaccurate well design. But say we wanted to design a well targeting this path. Of course, right, we would design this chocolate better, right? In a real case. And then let's say let's drape the facies prediction over that well path. So now in addition to say like the structural or the seismic hazards that might be identified from the well log or from the well path, you can also see what facies are expected to be encountered, right? So for this kind of like feature of interest here, we see that it's really the sand facies doesn't really kick in So about halfway down. So it would have probably been better to take the path and the dog leg down to somewhere around here probably, and then trace it, then follow the event, right? And what have you. But that's just to show one way of how you could leverage this, right, in operations. And with that, I will return and open the floor to questions. Okay, it seems to be something in the chat. Okay, so there's one question. Where can we find these apps and we should get help from programmers? Okay, all of this is done within a MathWorks product, right, called MATLAB, right? If you are licensed with MATLAB or you obtain MATLAB, you are able to get this workflow that I just demonstrated from the did I not show where the there I put in here, there it is, right? If you are if you have MathWorks MATLAB licenses for the right toolboxes, you can grab the code from this GitHub. Now, we also have built this into an app where you just need to point it to the data, right? And the workflow that we went through, right, is computed in the app, and then the output, right, are the predicted facies, right? You don't need to go step by step like we did today. Unfortunately, that is not available, right, through the GitHub. That would require either a technical engagement with the application engineering group at MathWorks or the consultancy group. What other is that clear, Ali? Okay, he must have dropped from the call. Okay, why combine? Okay, so Sanjeev is asking, why combine RNN and CNN and should be used as a hybrid approach? Should it be commonly used or specific to a field? The whole reason why we looked at something in addition to CNN approaches, which are typical, is just because of that. The existing body of literature showed good results using the image-based approach, but they were always limited, right, to the field and the data that it was trained on. We wanted to build something more robust and something that could generalize better, right? So we basically we're trying to develop a method where the cost function has as low bias as possible, because the lower the bias of a deep learning method, the better it generalizes. We wanted to avoid having to retrain every time new data or a new field is gone to. Now, of course, there's limits to that, right? This does well with carbonates and clastics in marine environments, right? When you go to land, when you go to onshore environments, if you have relatively flat sort of surface conditions, then it works well. But if you're into, say, a foothills, right, or a structured topography acquisition regime, then some transfer learning or retraining might be required. Okay, Mr. Ayon, sorry, does that answer your question, Sanjeev? Okay, I guess Sanjeev is left too, but this was and this is what's now called, when we did this, there was no terminology for it, right? So we just called it a hybrid approach, right? Now it's, I think, called ensemble learning is the broad domain where this would fall under now in the literature. Okay, Luis is asking, are these apps compatible with Petrel, Decision Space, or any specific version of these seismic interpretation platforms? MathWorks has a support package to plug into Petrel. And so we've been being able to plug into Petrel since 2020 or so. And about 3 weeks ago, I was talking with the development group, and they've recently liaised with Schlumberger, right, and ensured that upgrades were made for the current version of Petrel. Right now, there is no interoperability or connection capability with decision space software. Halliburton has not engaged us. We have just recently engaged with S&P Global to plug this and several other methodologies we have, like gamma ray auto interpretation and segmentation, proper uncertainty propagation within petroelastic inversion, and several things to bring into Kingdom. We're actively working with S&P Global to do that. And then we can also output all of this into various high-level languages, right? Into Python, into C, C++, JavaScript, right? I think if we push out to Python or to C++, you can plug it. You can get the SDK from OpenDetect, right, and plug it into DGB, or you can get the SDK from Icon and plug it into RockDoc. Okay, so does that answer your question, Luis? Okay, so must be losing people near the end. John is asking, when combining the RNN and CNN, can you explain a bit more on how the polling is conducted? Is it looking at the softmax value for both the CNN and RNN output? Yeah, that's exactly what it's doing. It's a simple polling algorithm right now. It looks at the softmax for the CNN, the softmax, right, for the RNN, right, for all the classes, right, and that class that has the highest mean of CNN and RNN score, right, becomes the class that's selected. Right now, we are actively working on improving that by using a neural network approach to combine and optimize the weights, right? Because right now they're both being treated as equal weight, right? So we're improving on that. Okay, Sanjeev's microphone was not working. Yeah, Louise responded, Ali responded on that, and John responded as well. Okay, if there are no further questions, I guess I'll hand it back to Mason.
Yes, Mazen.
Mason, sorry.
Yes, Mazen. So thank you Dr. Ayon for this informative and fruitful lectures. And thanks for all your volunteering efforts. I would like also to thank Dr. Mohammed Jawad Zain Abidin and our attendees. Okay. Dr. Mohammed, any last words?
Yes, Mr. Mazen, I think I can ask Dr. Ayon a question if he
Absolutely.
doesn't. Yes, Dr. Ayon, please, is there a possibility of collaboration between MathWorks and universities to train students from the geology or petroleum engineering departments?
Absolutely. We have a whole so MathWorks as a company has various divisions, right? So like government,
Yes.
defense, energy, all of this. There is a whole division called Edu or education, and their whole purpose, right, is to interact with post-secondary, right, university institutions globally.
Mm-hmm.
So what I would suggest is because I don't really have insight right into the EMEA organization, right? I can only speak for the US, so I'm not sure who the account rep and how the edu process works, right, in EMEA. So what I would recommend you do is you reach out to the account manager, right, in the region, and they can definitely connect you with the local with the local edu rep. If you find that challenging, or if you're unable to do that, please reach out to me, and I will liaise with some of my colleagues here in the office that work on the edu side to see what would be the best path forward, right, for the EMEA region.
Okay, great. Thank you, Dr. Yon. Mr. Mazen, maybe I can say some words.
Yes.
Dear Dr. Ayon Kumar Dey, on behalf of the SPWLA Iraq, we extend our sincere appreciation for your insightful and informative presentation. Your contribution has greatly enriched today's session. Mr. Mazen, we can close the webinar, yes? Or you have a
Yes.
question?
Well,
Okay.
I have a question. Okay, but well, actually, MATLAB is very well known in the Iraq market for many universities. Okay,
Oh.
they teach it. I believe Dr. Mohammed even can confirm that they teach it in university as a mandatory class.
Yes, yes.
Yes, yes,
Undergraduate students.
yes, and but from other side, okay, I don't believe it's used too much in its geoscience application. Like from what you see in this lecture, I can see from the visualization, from the output, input is it's reached to a very very advanced degree, you know. And before a few years, I start to see some kind of geoscience conference by MathWorks.
Yes,
If
we
I'm
have
not
the
right,
MathWork Energy Symposium in the
symposium,
fall
yes.
every year in Houston.
Okay. Because during, I believe, Corona time or after it, I start to
It was
see
virtual.
all,
Yeah.
virtual, and all the videos is there. I believe the video is still there for few
Yes,
years.
if you Google MathWorks Energy Conference or MathWorks Energy Symposium is what it's been called the last 2 years. It was the Energy Conference before that. You will find a link to videos. And in fact, the easiest way to do it is when I map that today's deck to PDF and send it to you. Those two customer success stories that were shown from Shell. Both of those were presented at MathWorks Energy Conference and Symposia over the last couple of years.
Yeah. I watch some of these videos. Okay. I'm not sure if there is in more new video because apparently it's become not virtual, it's become physical.
Yeah,
I'm not sure. This is
in
unfortunately.
person now.
I would really recommend this back to virtual because it was really great source how to use MATLAB in geoscience and energy application. I saw many application logging, acoustic analysis, many other, you know how to use, because if somebody come and like you have the basic of MATLAB, okay, and he want to make application for this one, these video is really good source. I remember even when I was working for Baker, like they was using MATLAB for NMR processing, signal processing for wireline data. Okay. In all cases, I believe we can conclude the lectures. Okay. Thanks for your time,
Indeed.
doctors.
And if you want to dive a bit deeper into the videos, we've completely revamped our energy resources page. So if you
Okay.
Google MathWorks energy resources, you'll come to an overview page, and there are many videos and many case studies and across the whole
Beautiful.
value chain. So not
Beautiful.
just geoscience, there's
That's great.
engineering, right, with
Mm.
production maintenance,
Mm.
reservoir engineering with production optimization, oil field optimization, right? So production data analysis, and then production optimization with particularly focused on multilateral pad drilling.
Yes, I remember like one time, like there was a project with Dr. Mohammed, like about
Yes.
using MATLAB with its AI features, okay,
Yes.
to find imputation data. And there is like some kind of AI model. You can
Yeah.
select all these models. Okay, I'm pretty sure now the version have been
Okay.
more developed. Okay.
For
I believe we can.
petrophysicists specifically, right? One application we've got, or one workflow solution we have that gets a lot of traction with the petrophysicists are you can bring in your well logs, right? Your raw logs, and then you can condition them in MATLAB. So you can remove the outliers, you can sort of spikes, right, and the cycle skips, right? The gaps you can fill in such a way that it is filled according to the local shape. So it won't just do say a linear interpolation, right? It will like look locally at how the signal is behaving, and then it will do a p-chip. Will do a p-chip interpolation, so that you not only get the data, but also you're preserving the local shape of the signal, right? And then and a very valuable thing you can also do is mitigate the coherent noise, so the machine noise, right? The wireline noise, and all of that can get mitigated. Normally, you just do random noise mitigation, but we can also handle non-random, right, or coherent noise mitigation. And then we bring that into we bring the gammas and the SPs into a automatic segmentation and labeling routine that will automatically segment and label those logs according to depositional motifs. So you can get it labeled as coarsening upwards, fining upwards, right? Shale, sand. And then that's brought into what we call our quick look dashboard. So then those logs are used to model the seismic response, model where in the seismic, right, the porosity lives, the fluid lives, and the lithology lives, what those signals should look like, right, if you were to acquire them from seismic. And then the final panel shows how you should optimally bin your data for seismic inversion if you want to chase petrophysical properties. So it's kind of a quick look dashboard for reservoir analysis and a feasibility analysis for petroelastic inversion. And a lot of the
This is really good.
petrophysicists in the Houston, the North Sea, and the Western Canadian Sedimentary Basin patches are actively using that, particularly the app form we have of it that they plug into Petrel. So they basically extend the capability of Petrel, right, by building an app in MATLAB and then plugging it in with the support package.
Really amazing. I just want to add a few things for the benefit of attendees as well. I guess I saw MATLAB start to link Python to its language? I saw
We
some
are
kind.
fully interoperable with Python. You can
Yes.
run Python in MATLAB. You can run MATLAB in Python. You can
That's
do it
great.
in live scripts.
Mm.
You can do it in Jupyter notebooks. You can do it in VS Code. So all the
Okay.
big
Yes.
environments.
Yeah, the second one, which is MATLAB or MathWorks YouTube channel, I believe it's very, very nice source for all. There is very long video, very short video. There is all type of video, all type of playlist. Okay, so if anybody want to learn MATLAB from zero to hero, I believe YouTube channel is really, really well established. Okay, if I'm
Yeah, our YouTube channel and our we also have a dedicated videos archive on within our own website, right? Both of those are excellent resources.
Okay, good to
That's
know.
great.
I saw also there is some kind of, I'm not sure free or not, but I believe it's free without certificate through Coursera. There's like a MATLAB
Yeah.
diploma
We
in
have
Coursera.
courses.
Uh,
We have courses and then individual courses in Coursera. I don't know if Coursera charges a fee, but we
No, I
do
believe
not
it's free.
charge a
Free.
fee. Yeah, we do
Yeah,
not charge a fee on
yes.
Coursera. So if there's any
Mhm.
fee associated, that's
It's
Coursera
for
making
Coursera.
up overhead, right?
Yes.
But
Yeah, because I attend this one. I didn't finish it, but I attended. It was really nice because it have several parts. It was free totally without certificate. If
okay, that's
somebody
excellent.
just want
So I
to
know
learn
that,
it,
and we have several courses, and we also have a learning path. So if you
yeah,
do
learning path.
a
Yes, learning
certain,
path.
if you do a certain number of courses in a certain order, right? At the end, you can claim to be like, okay, competent, right? Or you have developed, right, a competency in AI, in deep learning, in signals, in images, right? There's several pathways available.
Yes,
And then there's also
just
free training available on our website. The MATLAB Academy has many free on-ramps.
it's free.
All the on-ramps are free if you
Mhm.
go
There
to the
is.
MATLAB Academy.
It just come to my mind. I believe there is also one reservoir simulator called MSRT or something.
MRST, that's done by
Yes.
Syntef out of that's
Norway?
done by Syntef out of Norway. Yes.
Yes, and it's free. I believe it's free. I'm not sure. Okay, it's like reservoir simulator. Everybody can use.
Yeah,
And
it is
they
free,
develop it.
and it's a book. Another good asset is SHREM, Seismic Reservoir Modeling by Dario Grana and University of Wyoming. Has a great heavy on the petrophysics, right? A lot of petrophysics tools in that.
What
then
is
we
that?
it's called SHREM,
Sheer.
SERM, right?
Mhm.
It's from Dario Grana's group from Stanford, which is now at Wyoming. And then we are MathWorks personally is working with Jack Dvorkin, right, on developing petrophysics capabilities. Specifically, we're working on multimineralic, multi-phase fluid substitution Gaussman. So basically extending Gassman, biogassman to multi-mineral, multi-phase flow with the big goal being fluid detection in carbonates.
Mhm. Just one last question. In one of our lectures, I believe it was in Spotify, like they show they have some kind of dedicated what's so called agent or agent boot. It's only for this software. Like you talk with him and he do something for you regarding coding. So are there some kind of agent dedicated for MATLAB? Like ChatGPT agent, Copilot
We have an
agent.
internal. We call it Copilot, the MATLAB Copilot, right?
Okay.
And it is you can think of it as a closed fence, right? RAG Gen AI, right? So it is closed off from the internet, so it does not expose any customer information to the internet, nor does it pull from the internet, right? It completely does its retrieval generation from MathWorks resources, from our code, our examples, right? Our file exchange. It stops short. It stops short of source code, right? And things. So even when it's a bit inaccurate, right, or it might have a hallucination, it is self-consistent, right? It's hallucinating within, right, the MathWorks knowledge base. It's not like some random, right, Stack Overflow, right, like thing coming in. I just wanted to show you. I just wanted to show you here. If you go to the MATLAB Academy and filter by on-ramp, all of these on-ramps are free, right? So you can start here at the MATLAB on-ramp. So this is very basic if you have no experience or brand new to MATLAB, right? And it shows you basically how to use the language. Simulink, same thing, but so MATLAB is for technical computing. Simulink is for model-based design, systems engineering, right? And then you can take an on-ramp on machine learning, an on-ramp on physical modeling, statistics, optimization,
All free,
deep
huh?
learning. Yeah, look, app building, signal processing, multi-body. So this is for like if you hear robotic arms, so you want to automate processes. So for our industry, this is used quite a bit for the digital derrick, right? The automating. Equinor used this to automate, right, their North Sea humanless, right, rigs, and it takes you through every. You can get ramped up on wireless, object-oriented programming, right, computer vision, image processing, curve fitting, right. So you can see that there's quite a lot of learning resources available for free before you need to switch to any cost-based training.
Amazing. So I believe it was really a good lecture, and the information provided after lecture also really important. If anybody want to develop himself in MATLAB, I would like to thank you again.
I just put the link in the chat.
That would be great. Okay, so if anybody want to go to MathWorks, he can join this link. Thanks again, Dr. D, for your volunteering time. Thanks, Dr. Mohammed.
No problem.
And
thank you for asking and welcoming me.
And I would like to thank all our attendees. See you next month, inshallah, in our monthly SPWLA Iraq webinar. Thank you all. I will conclude the meeting. Bye-bye.
Goodbye.
عفوا. باي باي. مع السلامة.